So now that we have a prepared PDB file, it's now time to initiate our first design technique, which is the minimum flexible set. So the prerequisites for this are a molecular visualization software tool. I'll be using PyMol, and then also a software tool to visualize steric clashes. We recommend the protein design plugin. This is an implementation of probe dots for use in PyMol. This code is available on the Donald Lab GitHub page under protein design plugin. That source code is available here. Once this is downloaded and you have this up and running, you can open up that prepped PDB in the PyMol visualization. That's what we're looking at here. We have our protein target and our D-peptide here. So first thing, in order to visualize the steric clashes, we're going to hit sequence here on the bottom right. We're going to highlight our D-peptide, going to right click and hit actions, extract object, so that these will be two different objects, and you're welcome to rename this if you like. We're then going to use our plugin to visualize steric clashes between the D-peptide and the L protein. So we're going to come up to the top, hit Plugin, Legacy Plugins, Protein Interaction Viewer. And we want to look at dots. So we're going to hit Match Where Prepared. This is just the protein, and then also our D-peptide for selection 2. You can customize the dot and line sizes, which we'll see in just a moment. I'm going to leave the defaults as is, so hit Load Dots. We're going to close this menu. So let's actually look at the side chains. We're going to highlight both the peptide and the protein. Right click, show as licorice sticks. And I want to be able to differentiate the D-peptide from the protein. So I'm also going to highlight the peptide, color, secondary structure, hit that bottom option. I like any color choice is fine. I prefer these because they're much more visible. You may have noticed that a new object has appeared over here on the right called dots. If we hit this to expand, you'll see that we have small overlap, which are going to be these red and yellow dots. We have bad overlap, which are these purple dots. And then we also have van der Waals and hydrogen bonds, which are favorable contacts, which is blue and green dots. Right now, we're just going to look at bad overlaps for bad steric overlaps and clashes. Looks like we have one right here. So again, we're looking at in purple is our D-peptide and green is our protein. And it looks like this residue is clashing with our D-peptide. If we click on it, it will give us the amino acid and also its number. So like S291, 292, 293, S294 will set as flexible for our minimum flexible set. So let's go over to the Osprey interface and prepare this design so that we can alleviate this unrealistic steric clash. So I'm down in my downloads folder where I have Osprey, setup design. This time, instead of file import PDB, I'm now going to hit new confirmation space. And I'm going to use that Osprey molecule we prepared in the last video in order to actually create a confirmation space in order to alleviate this clash. So new confirmation space, going to go to DexDesign, that folder I saved. And then you'll see that the only option here is an Osprey molecule. The PDBs aren't visible in this menu. So we're going to hit open. A similar looking but different menu is going to appear. So you can see, note that we have a prepared molecule. You can see the bonds, you can see the hydrogens. Now here, instead of prepare, we have edit. So we're going to hit this edit in order to prepare this for the K-star algorithm. We're going to hit edit, and we're going to go first to confirmation libraries. So here is a very exciting feature. You can see here we have chain Y, which is our protein, chain A, which is our peptide, and we have the option to either add or add from file. And what we're adding here is the amino acid library for these different chains. So here we're going to assign for our chain Y, which is our L protein, I'm going to hit add amino acids. These are the 20 L space canonical amino acids. And then I'm going to go to chain A, which is our D-peptide. I'll add, and then D amino acids. Also note that you are welcome to customize and add your own amino acid libraries. You can add from file here. So we have our L amino acids for our L protein, and then our D amino acids for our D-peptide. Let's close this menu now. We're next going to go to flexibility. We're going to pass over mutations from now. The minimum flexible set seeks to alleviate steric clashes between our D-peptide and L protein without mutations. So we're going to come back to this when we visit and implement the inverse alanine scanning design technique. We're going to hit flexibility. And what we're seeing here is our flexibility editor. So I'm going to click over to the D-peptide first, chain A, and we're not setting any mutable residues currently on the D-peptide, but we would like to set translation and rotation of the ligand. So keep in mind we've aligned our D-peptide into the pocket where the pre-existing L protein was. So now we'd also like to translate and rotate to update to the new chemical context. We're going to add down here in molecule motions, and we're going to make sure that translation and rotation is checked. Note that it is now highlighted in the visualization. Settings here I'm going to leave as default, but you're welcome to change these as needed. I'm going to close this menu. Now note that translation rotation is labeled in the molecule motions. I'm then going to go over to chain Y, which is our protein, and I've already set translation rotation on the peptide, so I won't do it on the protein, but I do want to make that residue S294 flexible. So I'm going to come down here, I'm going to hit add, and then go to serine 294. And note here what we're looking at is the flexibility menu for our protein. If we click one of these residues and then close, note now that that residue says flexible, and there's now 19 conformations for those 19 conformations of serine. So we've set as flexible the residue serine 294 on the protein, given as shown here in the flex positions, and on the peptide we've set translation rotation on. So now that we've done that, let's close the menu. And now we need to actually save these so that we can run the KSR algorithm to find alternative rotamers and also minimize those rotamers to see what will alleviate those steric clashes while translating and rotating that D-peptide. So we're going to hit File. We're going to hit Save Conformation Space. I'm going to save this as minimum flexible set. I'll call it complex. So when we save that, it just saves the complex. We also need to individually save the protein and the ligand. So again, hit File, Split Conformation Space. What we have here first is our protein, which is our chain Y. So we'll click this, hit Save One Molecule, and this will just be saving our protein, which is that L space protein. Save one molecule. This is going to be minimum flexible set protein. Notice these are now .conf space files. And then we also need to save the ligands. We're going to uncheck the protein. I'll check the ligand, save one molecule, minimum flexible set ligand. I'll save this. Now that we're already here, let's go ahead and compile these conformation spaces. I already have the complex open. I've saved it just in case I need to revisit. So I'm going to hit Compile Conformation Space. We have one design position, that's serine. There's one sequence because we have no mutations, and there's 19 conformations because there's 19 retamers for that serine. So we're going to hit Compile. Now that it's compiled, I'm going to hit Save. I'll save this again as minimum flexible set complex and hit Save. We're now going to close this menu, and we're going to close out of the complex. Now we need to compile both of the protein and ligand. So we'll hit File. Instead of New this time, we're going to hit Open Conformation Space. Note, again, we now have these conf space files. Let's compile the ligand first. We can check that we've done this successfully because we just see the ligand in the visualization. Hit File. We don't need to do a split because we just have the one chain now, so we're going to hit Compile Conformation Space. Should have 0 because we don't have any flexibility in this, like we only have translation rotation. Compile, save, MFS ligand, save, close out of this, and then we're going to do the exact same thing on the protein. So File, Open Conformation Space, then flexible set protein, File, Compile Conformation Space. These all look correct. Save, minimum flexible set, protein. So now that we've compiled our design space, let's close this. We'll close out of the interface. And let's go to that directory where we saved all of those files. I'm actually going to organize this a little bit. I'll make a directory called flexible set and move all of these into that directory. So there's a number of things to note here. So we have our original input, which is in one directory up, this match prepared, and our minimum flexible set. We have our conf space files that we prepared, and then we compiled those. So these are compiled confirmation space, CCXS. Note, when we want to ensure that we have compilation for our complex, compilation for our ligand, and also compiled confirmation space for our protein as well. I recommend if you need to revisit any of these to ensure that you set flexibility or mutation, you can actually open these confirmation spaces back up into the interface quite easily. So you can just restart the interface, hit open confirmation space, and reopen any of these as needed. But now that we've gotten all that preparation out of the way, now it's time to run the K-star algorithm. So if we revisit our install of DexDesign, we go to back in our downloads folder. You'll notice that if we enter Osprey 3, there's an option for K-star, and I recommend reviewing this. It has all of the flags that are needed. So we're going to run /Osprey 3 K-star, our complex conf space, that's going to be our compiled complex confirmation space. Design conf space, this is going to be our D-peptide. This is going to be the ligand. That we're going to have our ensemble directory, and this is customizable. You can save the ensemble outputs wherever you like, the epsilon confidence level, and then there's other options as well, such as the maximum number of confirmation spaces, simultaneous mutants, and others. But let's just look at these first few for now. So what we're looking at here, I've now switched over and I'm logged into the cluster where I'm going to compute my K-star score. Some of this is going to be different depending on the hardware that you're using. So I'm setting my memory, partition, other things, a Slurm that I'll be calculating. Notice that I'm directing in the cluster to my DexDesign installation. I'm passing it the K-star command. The complex confirmation space is the minimum flexible set, our complex once again. Our target confirmation space, what we're trying to bind to, is going to be our protein, and our design, once again, is our ligand. Naming the ensemble directory where I like all the outputs to go as ensembles, my epsilon, so confidence level is 0.9, and then this flag is the maximum number of simultaneous mutations. I just default to 10,000 every time, but this doesn't actually matter in this instance because we're not doing any mutations. And then I'm just doing a little bit of cleanup and message passing afterwards. So once that's run, I'm going to look at the output file, and we have a printout of all of the energies of the residues, which are quite helpful. These are also available if we go into the ensemble output directory. You can also see these in these CSV files here alongside the output PDB file. Note the notation here is 294 serine goes to serine. The residue is first listed in all uppercase as being flexible, and then it's also in lowercase, indicating it's a flexible residue and not mutating. If this had been mutated, this would be all in uppercase and a different identity. So let's look again at that output. And I actually recommend opening this up in an Excel file because it's much easier to look at. Copy it over here. So let me just copy the K-star output, open up an Excel file, copy and paste it in. We should go to data, text to columns, and these are delimited by commas, so delimited, comma, finish. And now this is going to be much easier to read. So again, just double check we have flexibility. And then all these other columns are outputs. So we have our K-star score, which is starting on a log 10 scale of 12.775. We have our lower and upper bounds. We have the partition function lower bound for our complex, the partition function upper bound for our complex. Number of confirmations is 19. The difference in the upper and lower bound for our complex is 0. We have our ligand partition function lower bound. We have our ligand partition function upper bound. And we have one confirmation on our ligand because there was no flexibility, just translation rotation. And again, the difference between our upper and our lower bound on our ligand is 0. We also have our protein burden function upper and lower bounds. We have 19 conformations on our protein, and again, the difference between the upper and lower bounds of our protein in this case is 0. So now that we've looked at the data and we see that we're getting some predicted binding, let's actually look at that protein output structure. So I'm going to go to the ensemble output. I'm going to download and open up this file in Pymol. All right, so I've downloaded that file. I've now opened it up in Pymol. You may notice that it looks really odd. The secondary structures are off. Pymol sometimes gets a little bit confused on secondary structures. If it looks like this, you can type DSS, and it will reassess the ensembles and give a better secondary structure visualization. So again, we have our L protein, our D-peptide, it's at sequence. And again, we're going to do that same process we did earlier. We're going to extract out our D-peptide. You're welcome to rename if you like. Let's go ahead and go to our plugin, load dots, look between our protein and our D-peptide, load our dots. And let's make this a little bit easier to look at. Go to dots again, and let's see if we've alleviated that bad overlap. S294, which we have. It was previously here. This is now changed rotamer identity. We've also translated and rotated the ligand. We've now alleviated that steric clash, and note that we don't see any other bad overlaps between the peptide and our protein, which is excellent. You'll note actually that we now have 10 different states here. If we hit the play button on the bottom right, we can actually see the change in conformation between each of the conformations of this ensemble. So we can see the rotameric state of the serine 294 changing. We can also see the D-peptide translating and rotating in that pocket as well. So we've now successfully performed the known flexible set. We've looked at our D-peptide in conflict with our L protein. We've assessed for steric clashes, and we've now used the K-star algorithm and its ability to change the conformations of structural data to alleviate that clash, and then we now have something that has a predicted weak binding affinity that we now like to optimize. So now we're going to use this minimum flexible set for inverse alanine scanning.